Assalamualaikum everyone. In today's video lecture, we learn about potentiometry under the course of pharmaceutical analysis. So let's start. So first of all, we need to learn some common terms regarding potentiometry. Electrolytes, a substance which dissociates into ion as a result of passage of electric current through its aqueous solution is known as electrolyte. Then electrodes. An electrode is a small piece of metal or other substance through which an electrical current enters or leaves an electrolytic cell or other medium. For example, copper electrode, zinc electrode. So it can be of two types like anode and cathode. Anode. The electrode connected to the positive terminal of the battery attracts the negative ion and through which the electricity is supposed to enter the solution is termed as anode. So anode is positively charged. In other words, anode is electrode where oxidation takes place. Okay, and cathode is just opposite to anode because here reduction takes place and cathode is negatively charged. Mechanism of electrolysis. Due to the presence of electricity through an electrolyte solution, the electrolyte is dissociated into two ions, cations and anions. The cation migrate to the cathode from a neutral atom by accepting electron from it. So from the name cation, actually cathode comes from because cation is attracted by cathode and hence cathode is negatively charged. The anions migrate to the anode and yield a neutral particle by transfer of the electron to it. As a result of the loss of electron by anions and gains of electron by cation at their respective electrodes, chemical reaction takes place. So here is a diagram of electrolysis has been shown. It shows the anode, it shows the cathode, this is the media. So electrochemical cell, a device for producing an electrical current from a chemical reaction is called an electrochemical cell. Then half-life, sorry, half cell. Each half of the electrochemical cell where oxidation occurs and the half where reduction occurs is called half cell. Current, the flow of electrons through a wire or any conductor. Then redox reaction, a reaction which is brought about by loss of electron or gain of electron simultaneously is called a redox reaction. Then actually there are two types of electrochemical cell. One is galvanic cell where current is produced and another is electrolytic cell which utilizes electricity for uh, uh, analysis. Okay, so they are just opposite to one another. Okay, so here we can see the differences between galvanic cell and electrolytic cell. Chemical energy is transformed into electrical energy in these electrochemical cells. Here, electrical energy is transformed into chemical energy. The redox reaction that takes place in this cell are spontaneous in nature, and in input of energy is any input of an energy is required for the redox reaction to proceed in these cells. That is, the reactions are non-spontaneous. So in galvanic cell, the anode is negatively charged and the cathode is positively charged, where in electrolytic cell, this is opposite. The electrons originated from the species that undergoes oxidation, electrons originated from external source. Now let's discuss the galvanic cell. In galvanic cell, the cell in which electrical current is generated by spontaneous redox reaction is known as galvanic cell. A simple voltaic cell is shown in the figure. If we conduct the zinc and copper by means of a metallic conductor, the excess electrons from the left cell will be able to flow through the external circuit into the right electrode. The net reaction is the oxidation of zinc by copper. So these reactions takes place. You can see here, uh, the zinc anode uh, and the copper. These are the zinc anode and copper cathode. Then cell reaction. Cell reaction is the overall chemical reaction occurring in the electrochemical cell. It is the sum of the two electrode reaction. Cell potential. In a voltaic cell, electrons are released at the anode and it becomes negatively charged. The negative electrode pushes the electron through the external circuit by electrical repulsions. The flow of current through the circuit is determined by the push of electrons at the anode and attraction of the electrons at the cathode. These two forces constitute the driving force that sent electrons through the circuit. The driving force is called the electromotive force or cell potential. The EMF or cell potential is measured in the unit of volts and is also referred to as the cell voltage. So representation of a cell has been shown here. First of all, single vertical line. You can see there is a single vertical line between zinc and zinc ion and copper ion. So single vertical line represents the phase boundary between the metal electrode and the ion solution, because zinc is electrode and zinc ion is the solution. So this is the anode half cell and this is the cathode half cell. Okay, so this is usually for galvanic cell. So this shows the interface between these. Okay, so the anode half cell is written on the left and the cathode half cell is written on the right, and actually their position is also left and right, and sometimes it is called E right and this is called E left. A double vertical line represents the salt bridge. Okay, so between them a double vertical line sometimes used. It represents the salt bridge, porous partition, or any other means of permitting ion flow while preventing the electrolytes from mixing. Anode half cell is written on the left and cathode half cell on the right. So in the complete cell diagram, the two half cells are separated by a double vertical line in between. Okay, so this is the salt bridge. The symbol of an inert electrode, like a platinum electrode, is often enclosed in a bracket. Sometimes calomel electrode, mercury electrode, platinum electrode are used. Okay, so this is a standard electrode. Sometimes they are used. If they are used, then they are kept in a bracket. The volume of the EMF of cell is written on the right of the uh, cell diagram. So the voltage is sometimes written on the right diagram. So calculating the EMF of a cell, the EMF of a cell can be calculated from the half cell potentials of the two cells by using the following formula. So E cell is equal to E cathode minus E anode. This is the overall formula. Sometimes you can write this as E down minus E bump, that is E right minus E left. Whereas E right and E left are the reduction and oxidation potential of the right-handed and left-handed electrodes respectively. So predicting the feasibility of the reaction. For example, if the EMF is positive, then the reaction is feasible, and if EMF cell is negative, the reaction is not feasible. So this is the overall phenomena. So we always deserve positive. Okay, the EMF of the cell is negative, then the cell cannot be constructed. Okay, here you can see its value has been negative, so it cannot be constructed. It's not stable one. Now we'll discuss one of the equations for determining the EMF of the cell, that is Nernst equation. In 1889, Nernst derived a mathematical relationship by which we can calculate the half cell potential from the standard electrode potential and the temperature of the cell. This relation is known as Nernst equation. So that is equal to E naught plus 2.3 RT divided by NF into log K. So their name has been shown here. Just go through this. So how we will calculate this? So go through this equation, and you can see a derivation. You can see here there is a derivation, but we need to see the ultimate derivation. So this is the ultimate value is equal to E naught plus 0.0591 divided by n, because you know RT. Okay, R is there is a value of R. Okay, and you know T value is 25 degrees Celsius. Okay, then NF 1 Faraday means 965,000 coulomb. So if you put the value, you will find RT by F value is equal to what is equal to 0.0591. Okay, so this is the overall calculation. Now one of the important diagram for determining the uh, reduction potential, usually this is the reduction potential. Okay, reduction potential is positive for these compounds and negative for these. Usually this is negative for the metals and positive for the non-metals. Okay, mostly non-metals. You can see here most of them are non-metals, and here most of them are metals. Okay, so we always know that metals are strong reducing agent, and non-metals are oxidizing agent, like oxygen, chloride, fluoride. Okay, these are oxidizing agent. Okay, this means these are reducing agent and these are oxidizing agent. Now what this E potential means? Okay, this E value means the potential. Okay, the tendency, the more reduction potential one compound will have, the more would be its tendency for reduction. Okay, so these compounds have higher tendency for reduction because they have positive value for uh, reduction. Okay, so they have higher reducing potential, that means they have higher tendency for reduction. That means something that is having higher tendency for reduction, they would be reduced. Okay, so something that is reduced would be the oxidizing agent. So these are strong oxidizing agent. So oppositely, these would be the strong reducing agent. And this is the overall phenomena. You can see here their tendency for capturing electron is very high. Okay, so all of them is capturing electron because in this list we have shown the reduction potential. So reduction means accepting electron. So all of them is accepting electron. Fluoride, manganese, chloride, oxygen, bromide, iodide, cadmium, nickel, zinc, aluminum, magnesium. All of them is taking electron. Why? Because we have shown reduction potential, and reduction means receiving electron. Okay, so they have received electron, but their tendency for receiving electron is not same for all, because you can see they have positive value, so their tendency for receiving electron would be higher. Okay, their tendency for receiving electron for would be medium, and their tendency for receiving electron would be the lowest. Actually, they don't actually receive electron. The electron is received by these agents. Okay, because they are have higher tendency. That is why these are the compound which will take electron would be the strong oxidizing agent. So that's why fluoride, oxide, chloride, these are strong oxidizing agent, and in contrast these are strong reducing agent. So I think you have easily understood this. So now reduction potential. So reduction potential is the measure of how thermodynamically favorable it is for the compound to gain electron. A high positive value for a reduction potential indicates that a compound is readily reduced and consequently is a strong oxidizing agent. For example, it removes electron from the substance with lower reduction potential, and the oxidized and reduced form of the substance is known as redox pair. So a substance with high reduction potential will oxidize one with uh, lower reduction potential. So here a math has been shown. Go through this. I think you can easily perform the math. Just put the values here. All of the values here has been given. Always keep in mind that which one would be the anode and which one would be the cathode. The anode always would be the faster one. Okay. So this is the one which would be used as anode, and for the anode we will the equation is Edan minus Ebam. Okay, E right minus E left. Okay, I think you can easily do this math. So EMF is positive. That means yes, the reaction is feasible. Okay, so another formula has been shown here. So what is potentiometry? It is the measurement of electrical potential by means of a potentiometer. It's called potentiometry. It's used in electroanalytical chemistry, usually to find the concentration of the solute in solution. So general principle, a typical cell for potentiometric analysis has been shown here. So this is the reference electrode and this is the solve bridge for calculating the EMF. So potentiometric titration. A potentiometric titration involves measurement of the potential of a suitable indicator electrode as a function of titrant volume that causes a rapid change in potential near the equivalence point. Potentiometric titrations are not dependent on measuring absolute value of each cell. Potentiometric titration result in depend on titrant having the accurately known concentration. So actually, in previous acid base or aqueous titration is usually performed this titration. Okay, where the endpoint comes, actually this change appears. So in potentiometric analysis, reference electrodes are used. A half cell with the accurately known electrode potential, that is EREF, that is independent of the concentration of the analyte or any other ion or in the solution, always treated as left-hand electrode. So standard hydrogen electrode. The standard hydrogen electrode, the reference against which potential are compared. The standard hydrogen electrode develops a potential which is arbitrarily considered to be zero, and all other electrodes develop a potential which may be positive or negative compared to the standard hydrogen electrode. So indicator electrode which is immersed in a solution of the analyte develops a potential in indicator that depends on the activity of the analyte. It is selected in its response. The indicator electrode responds rapidly and reproducibly to change the concentration of the analyte ion or group of analyte ion. Examples of indicator electrode are noble metal, glass membrane electrode, cone hydrogen electrode, antimony electrode. So noble metal. Several inert conductors can be used to monitor redox systems such as platinum, gold, palladium, and carbon. Salt bridge. So one of the important concept, because salt bridge is almost necessary for any other cell. The salt bridge is like a U-tube filled with an electrolyte such as NaCl, KCl. It provides a passage to ion from one compartment to other compartment without extensive mixing of the two solutions. With this ion flow, the circuit is complete and electron pass freely through a wire to keep net charge zero in the two compartment. Potassium chloride is nearly ideal electrolyte for the salt bridge because the mobility of the potassium ion and chloride ion are nearly equal. So function of salt bridge: it connects the solution up to half cell and completes the cell circuit. It keeps the solution into half cell electrically neutral. In anode half cell, the positive ion pass into the solution and there shall be accumulation of extra positive charge in the solution around the anode, which will prevent the flow of electron from anode. This doesn't happen because negative ion are provided by salt bridge. Similarly, in cathodic half cell, negative ion will accumulate around the cathode due to the deposition of the positive ion by reduction. To neutralize this negative ion, sufficient number of positive ion is provided by salt bridge. Thus, salt bridge maintains electrical neutrality. It prevents liquid-liquid junction potential. So we'll discuss in upcoming slides what is liquid-liquid junction potential. That is the potential difference which arises between two solutions when in contact with each other. So liquid-liquid junction potential. If in a cell two electrolytic solution or two solutions of the same electrolyte but different concentration are in contact, the more concentrated solution tend to diffuse through the barrier. As a result, potential difference is usually developed across a boundary between two solutions. Such potential is called liquid junction potential. For example, a liquid junction consisting of one molar HCl solution that is in contact with the solution that is 0.01 molar HCl. Both proton and chloride ion tend to diffuse across the inert porous barrier. Proton ion diffuse more rapidly than chloride ion and a separation of charge result. The potential difference resulting from this charge separation is the junction potential. The magnitude of the liquid junction potential can be minimized by placing a salt bridge between the two solutions. A saturated solution of the potassium chloride is good from both standpoints. The mobilities of the negative and positive ion are nearly equal. The net junction potential in such bridge is typically few millivolts. Actually, liquid junction potential is found due to the concentration difference. Okay, it can be due to the ion difference. Okay, there a simple potential is generated. Is uh, few millivolts. It can be few millivolts, but these few millivolts can also have impact on the overall EMF. Okay, so advantages of potentiometric titration: it provides more reliable data than the usual titration method, useful with colored or turbid solution, useful for detecting the presence of unsuspected species, and may be automated. So there are four types of potentiometric titration, like acid-base titration, redox titration, complexometric titration, and precipitation titration. Just to go through this, you can easily understand this because I have several lectures on these topics independently. Okay. So what are the common applications of potentiometric titration? So in determination of assay of API like sulfur diazine, ketoconazole, lidocaine, chondroitin sulfate, then determination of assay of excipients, for example, surfactant, determination of water in API, excipient, and finished product, determination of minerals and chelating agents present in pharmaceutical preparation, for example, minerals such as zinc, chromium, copper, iron, aluminum, zirconium, calcium. Okay. So this is the overall lecture from potentiometry. If you have any confusion, please inform me in the comment section. Thank you.